Dear students, in this video, we will look into one of the most important methods to solve linear programming problems in n variables, and we would call it as a simplex method. So the idea of simplex method is to jump from one basic feasible solution to another basic feasible solution in such a way that whatever value of objective function we obtained at first iteration, we keep on improving as we are jumping from one objective function, one basic feasible solution to another basic feasible solution. And idea is that as we are continuously improving a method, if we know a way to terminate, that where we should stop, that is always going to be a better solution than the previous ones, because that's the basic intuition behind simplex method. And another thing is that the way we would be jumping, we would always ensure that our solution is basic feasible solution. To ensure that we have basic feasibility, we always keep in mind that all variables, be it slack or surplus or decision variables on which we are setting up our optimization problem, they have to be greater than equal to 0, and that is the premise with which we are setting up our problem. And of course, constraints would be satisfied because we would be putting everything as an equality constraint, and when we put everything as an equality constraint and solve a system of equation, the solution, if it exists, is definitely going to satisfy those conditions that we have started with, stated in equality form. So the basic steps that we will try to learn slowly in this fundamental method is that we will have a canonical form. So using that canonical form, we can easily calculate the solution. So that would be our first basic feasible solution. And we can calculate the value of objective function corresponding to that first basic feasible solution. Then we will learn a rule that we have to go from one basic feasible solution to another basic feasible solution. Number of equations are not going to change. Number of variables are not going to change. So number of variables that we have to declare equal to 0, they are not going to change. So if we have to jump from one basic feasible solution to another, we would make sure that one variable enters. That means we will try to make it non-zero, and as this one variable enters, another variable has to leave, so that we always meet these conditions of m minus n variables declared as 0. So we have to identify this variable that is entering and one variable that is leaving in such a way that these two conditions, that is our solution is improving until we meet a termination criteria, and we go from one feasible to another feasible are met. And these two steps, they are essence of simplex method. And while most of the textbooks that deal with applications preferably skip the derivation part, but here we will pay some attention to that, as it is core of the method, is that why this is working. Finally, at each step, we will keep on having a variable that is entering, that is leaving, and each step we will keep on calculating the updated value of our objective function f prime, f double prime, f triple prime. These are not derivatives. They are just saying that how the variable value are getting updated as or the objective function values are getting updated as variables are entering and leaving. So this is not to be confused with derivative. Then we will deal with the minimization problem as a standard problem. You can also think about how to deal with maximization problem, because it would be exactly opposite thinking, but step would remain same. So when I say that it is exactly opposite thinking, let us look into that. So if we have an objective function stated as a1 x1 plus a2 x2 plus an xn, and we have to make some variable 0 So we will have some variables which would be declared as non-basic, and we will by default set them to 0. So that all these are zeros and they become non-basic. And we would have some other set of variables which would be set to basic, which are not set to 0, and we will calculate the solve the m equations with respect to those m basic variables. Now, if we have to make one non-basic variable as non-zero at the cost of another basic variable, it is quite clear that since it is a minimization problem, if we choose a variable that has a negative coefficient, we should try to make it non-zero first. For example, if our objective function is 2x1 minus 3x2, if both x1 and x2 they are equal to 0 at first iteration, and at second iteration you have to make one of them non-zero, subjected to the condition that objective function's value should decrease and x1 and x2 should be greater than 0. You can clearly see that if you increase the value of x2, value of f is going to decrease rapidly because it has a minus sign here. So minus 3, whatever the value we would get other than 0 or greater than 0, value of objective function is definitely going to increase as there is a negative coefficient present here. So our first preference would be to make a variable which has a negative coefficient in front of it as non-zero, as it will result in faster change in the value of objective function towards our desirable range. So because we have to meet this condition, that first solution should be inferior to the second solution as we keep on progressing. Also, if it becomes a maximization problem, then you would not choose this minus 3x2, because if you make x2 as positive, there is a negative coefficient, it would result in decrease of f. But now objective function deals with maximization of f if we deal with the second kind of problems. So in that case, I will choose a variable which is of the largest positive value, which is 2 in this case, so that if I increase the value of x1, my f overall increases. So in the case of minimization, looking at the negative coefficients would be our of first interest, and this will become more clear as we progress further. So let us set up a system of equations. I will set up an abstract system so that we develop a mathematical intuition about that. So let us say that we have m equations and we have n variables, and our m is less than n. Let us say that we already start with the canonical form, and this canonical form is coming thanks to our slack or surplus variables or artificial variables that we will introduce. And initially, let us say that we have introduced m slack variables as all these equations were in less than equal to form. So our first equation comes out to be 1x1 0x2 up to 0xm. Second should be 0x1 plus 1x2 plus 0xm. Third should be 0x1, 0x2, 0x3, and so on up to 0xm. So I can generalize these equations as 0x1, and only the mth term should have one coefficient and everything else is equal to 0, 0xm, 0xm, this would be 0x2, and so on. So this is for those variables which we have would declare as non-basic, because we want our first solution to be readily available to us. Then we will have another n minus m variables declared as non-basic so this would be basic. I'm sorry, because we will not set x1 x1 equal to 0, so we will call them as basic variable, and other variables would be set as non-basic, which we would put the first value as 0 to get the first solution that is readily available. So we would have a1 m plus 1 x m plus 1 plus a2 m plus 1 x m plus 1, and so on. So it would be a1 n x n plus a2 n x n, and last row can be written as a m m plus 1 x m plus 1 all the way till a m n x n, and these are equal to, so let me write it little in a little bit compact form. So this is equal to b1, b2, all the way till bm. And if we have to identify the solution, so this would be b3 and so on. So if we have to identify the solution readily, we said that these are non-basic variables. We can set all these non-basic variables xm plus 1 to xn to 0, and you can clearly see that x1 equal to b1, x2 equal to b2, x3 equal to b3, and so on. So this is our first solution which is readily available. Also, we will make our objective function as one more equation here. And you know that in objective function, none of these slack variables will appear because objective function has nothing to do with constraints as far as slack variables are concerned. So we can write our objective function in a way that it looks like cm plus 1 xm plus 1 c m plus 2 xm plus 2 all the way till cn xn, because all these variables would be part of our objective function and its value is equal to f. So if we bring our f here, it becomes minus f and this becomes 0. So if you look at the first basic feasible solution, as we are putting xm1 plus 1 all xn equal to 0, our value of objective function directly becomes the right hand side, and we can say that whatever is the value we have here, because these terms would vanish as we put all these variables as non-basic, so our objective function value is whatever we have on the right hand side. Now let us try to identify that this is one feasible, basic feasible solution such that our x1 equal to b1, x2 equal to b2, xm equal to bm, and this constitutes our basic solution. Our non-basic solution would have anything and everything xm plus 1, xm plus 2, xn equal to 0. Anything and everything with index greater than number of equations we set to 0 initially. Now we have to go from one basic feasible solution to second basic feasible solution. So to do that, we will select that variable from xm plus 1 to xn whose coefficient is the largest with negative sign. And we already discussed the rationale behind that. So let us say that we choose xs where s is greater than equal to m plus 1, which means that the index is somewhere here. We will select a variable to go and become non-zero, and this xs should be selected in a way that when we look at objective function, this coefficient cs should be largest negative number, and that would ensure that our jump or improvement in solution is the best. Now when we do that, let us try to see what happens in first equation. So if we say that we have made everything else is has zero coefficient up to m terms, so we will ignore that from first equation. Now our term s is getting activated, so a1s xs is equal to b1. If we have to make it non-zero, then we can say our x1 is equal to b1 minus a1s xs. Our x2 is equal to b2 minus a2s xs. Our xm is equal to bm minus ams xs. Now, if we have a negative coefficient in front of objective function as Cs, if we increase the value of xs from 0 to some positive number, our value of f is going to decrease. That is very clear to us. And then what we do is we see that how much we can increase the value of xs such that x1 stays non-negative, because we have to always stick to a basic feasible solution. So we say that whichever would hit the zero first, we cannot go beyond xs from there. So for example, if value of xs equal to 2 makes this equal to 0, whereas this equation becomes 0 if xs is equal to 1. So if we increase the value of xs slightly beyond 1, our basic solution of x2 is going to get negative, which is not acceptable. So we would say that we will have entering variable decided by sign of our objective function, whereas the exit variable that would leave and become part of non-basic variables or would be set to 0 should be minimum of bi upon ais, such that ais is greater than 0. Because if this coefficient, for example, itself is less than 0, so let us say that coefficient here is negative, then it does not matter, you keep on increasing the value of xs, this term negative multiplied by a negative sign is going to get positive. This equation is never going to become 0, it is always going to stay positive, and this equation would ensure that the solution is not bounded by that equation, because there is no risk of getting this equal to 0. So our limiting factor would be bi upon ais, such that this ais is greater than 0. Now once we do that, we can always say that our new solution would be our xs would take value of xs star. Our other variables would become bi double star, or let us stick to terms of bi minus ais xs star, where value of xs star is guided by the fact minimum of bi upon ais, because that's much we can increase xs star. So this is minimum of bi upon ais, and other variables would get changed by bi minus ais xs, because all these equations would have to be satisfied, because now xs has entered into solution. So all these x1, x2, x3 up to xm, they have to adjust their values. So for all those variables, we would have the updated value. Our xr would be equal to 0, where r is equal to j plus 1 all the way till n, but r cannot be equal to s, because s has already entered into our basic feasible solution now. Also, our objective function here would have a new value, let us say, which is represented by f naught dash, such that f naught dash is better than f. I am not saying greater or minimum, because you can set this problem both for maxima and both for minima. Now let us try to quickly go to an example before you get lost into the equation, so that everything starts making sense to you. First of all, we are doing it hard way, and then we will make it an easy way. So let us say our question is minimize f equal to minus x1 minus 2x2 minus x3 subjected to 2x1 plus x2 minus x3 less than equal to 2, 2x1 minus x2 plus 5x3 is less than equal to 6, 4x1 plus x2 plus x3 is less than equal to 6, such that all xi's x1, x2, x3 have to be greater than equal to 0, and I varies from 1 to 3. So now we will proceed in steps. Our first step would be to change all these inequality constraints to equality constraints, and since all these constraints are less than equal to, what we will do, we will introduce a slack variable. As soon as we introduce slack variable, we can write this as 2x1 plus x2 minus x3 plus x4 equal to 2. 2x1 minus x2 plus 5x3 plus x5 equal to 6. 4x1 plus x2 plus x3 plus x6 equal to 6. These x4, x5, x6, they are slack variables which we have introduced to make these inequality as equality constraints. We will also write our objective function here, minus x1 minus 2x2 minus x3 minus f equal to 0, because f is equal to minus x1 minus 2x2 minus x3. Now if we focus on x4, x5, x6, we see that in terms of decision variables plus slack variables, we already have a canonical form, as these terms are appearing only once in these set of equations. So we will draw demarcation lines between our objective function and the constraints. So what we have, our first basic feasible solution is all set. We will say that x1, x2, x3 can be equated to 0, and hence we say that these are non-basic variables to begin with. And we say that our x4 comes out to be 2, our x5 comes out to be 6, and x6 also comes out to be 6. And since x1, x2, x3 is equal to 0, value of our objective function is also going to be 0. So we clearly see that this is basic feasible solution because all conditions are satisfied. x1, x2, x3 are greater than equal to 0. But we can do better, because in this case our value of objective function is coming out to be 0, as x1 equal to 0 equal to x3 equal to 0. So, and if we make x2 slightly positive, our value of objective function will drastically go beyond 0, and hence any negative number is minimum than 0, or of course positive numbers. So what we will do, we will try to swap a variable. That means we will make one basic variable as non-basic, and we will bring one non-basic variable from here and make it a basic variable. So as if you look at this equation, our choice definitely goes towards x2, because we should increase x2 to reduce the value of objective function. So we have zeroed down upon our entering variable. So we say that a variable that is going to enter now is definitely x2 in this case. Now, since we have this x2 as our entering variable now, we can say that x4 from equation 1 can be written as 2 minus x2. x5 can be written as 6 plus x2, and x6 can be written as 6 minus x2, because now we have made x2 as non-zero, and hence we are expressing everything keeping x1, x3 still equal to 0, x4 in terms of the other variables. Now how much we can increase x2 so that our x4, x5, x6 all remain greater than equal to 0? So in this case, this is not going to create a problem, as we can, if we increase x2, this x5 is always going to be positive, and we need to increase x2 to decrease the overall objective function, because coefficient of x2 is negative. So if we make x2 equal to 2, what we are going to have, x4 is 0 and x5, so x4 would become 0, x5 would be equal to 8, and x6 is going to be 4 in this case. So the maximum we can make x2 is equal to 2, because you try to increase this to 6, this term is going to get negative. It would be 2 minus 6 minus 4. So we are going to go towards a non-feasible solution, which is not acceptable. And hence we say that our second feasible solution comes out to be x2 equal to 2, x5 equal to 8, x6 equal to 4, and this is our basic solution. And our non-basic solution would be x4 equal to 0, x1 equal to 0, and x3 equal to 0. So now what we will do, we will do the pivoting about x2. So when we do pivoting about x2, our idea is to make all the coefficients in the column of x2 as 0 except 1. So we would write this as 2x1 plus x2 minus x3 plus x4 equal to 2, 4x1 plus 0x2 plus 4x3 plus x4 plus x5 equal to 8, 2x1 plus 0x2 plus 2x3 minus x4 plus x6 equal to 4, 3x1 plus 0x2 minus 3x3 plus 2x4 equal to 4, and our objective function was also an equation. So we will update the coefficients when we do pivoting operation as 3x1 plus 0x2 minus 3x3 plus 2x4 minus f equal to 4. Mind it, I am not doing anything special. I am just doing some basic row and column manipulations here so that we pivot about x2 now and make the first coefficient as 1 and everything else as 0. How I decided upon x, the first coefficient, as I have to make 1 because x4 was present in the first equation and x4 left the solution because we said that when x2 becomes 2, x4 has to be 0. So that gives us an indication wherever x4 was present initially as a pivot element, please go behind it and make that and do the pivoting around that particular row or equation. I will also tell you a shortcut to do this pivoting really fast, and that would be an easy way to do all these problems. Now in this case, if you, the reason we again do pivoting is that solutions become much easier. What we will do, x4 equal to x1 equal to x3 equal to 0, x4 x3 x1 equal to 0, which implies our basic solution comes out to be x2 equal to 2, and again here we will see that x5 comes to be 8 because x1 x2 x3 and x4 all put equal to 0, x4 x1 x3, and we already calculated x2 has a coefficient of 0, so that's why this term also reduces to 0. X5 comes to 8 and x6 comes to be 4. So this solution is exactly same as what we derived here, that is just by looking at how much we should change x2 and so on. Now if you put these values of x2 into objective function, we see that the minimum value that we are going to get in this case is f equal to minus 4. In step 1, our f was equal to 0. We are doing a minimization problem and we have already landed up with minus 4. Another good thing that this pivoting operation gives us is that in canonical form, it is very easy for us to identify that what should be our entering variable. Now, this should be our entering variable minus x3. If we make x3 as non-zero, and increase its value of objective function is going to get reduced further. And what should be our exiting variable? So what we will do, we will look into the coefficients here and these beta terms here. So what we will calculate is the ratio of 2 upon minus 1, 8 by 4, 4 by 2, and minus 4 by 3. We learned that when coefficient is negative, we are least worried because this term is always going to stay positive. Hence, we would not look into this, we would not look into this, and minimum of these two. Both these values come out to be 2, 2. So it's our choice whether we want to make x5 leave or x6 leave, because if first equation belongs to x4, second belongs to x5, and third belongs to x6. So if we say that, okay, this should be our leaving variable, that means we are implicitly saying that we will make x5 equal to 0 and solve for x3 and make x3 non-zero, and we will end up with a new set of basic feasible solution which was going to be better or at least equal to minus 4 in terms of the objective function. Now, this maths looks a little bit complex, but in the next video, I will introduce a tableau method to look into problem of simplex that will simplify all the calculations. But there are two key takeaways. First objective is to identify the entering variable and exiting variable in a way that we are always improving the solution and we are never leaving the optimality and that's why we bet on the minimum of b upon a, where a is the coefficient of columns in the entering variable.